Hello, this is Mrs. Piekarski. I'm recording this video for any of my students who are absent on, let's see, Tuesday, no, this is April 28th. Anyway, so just to get started, I don't think you have this page in your notes anymore, but I just want to show it to you, and I want to show kind of what happens to get these four shapes that we're going to get. So basically what we have is we have two cones. You have one cone the two cones are joined right at the very tip of and you have a plane that you're going to cut into those two cones with. And depending on the angle that you cut at, if you're at exactly 90 degrees, then you get a circle. And then as you're changing the angle of this plane, it changes the type of let's see, hold on, let me rewind this. It changes the type of conic that you're going to get. So let's play that again. So here we have a circle, then an ellipse, then a parabola, and then as the angle is changing, you're going to come into a hyperbola, and then basically we get a line, and then eventually an ellipse again, and then back to a circle. Okay, so that's what we're getting when we have two cones and we're cutting the cones with a plane with some angle to it. So we have a circle here, an ellipse here, a parabola, and then a hyperbola. Okay, very similar shapes. The difference between a parabola, where you only have one little loop, you have with a hyperbola you've got two, and they're going in opposite directions. Okay, so this will give you kind of a quadratic formula. Will give you the parabola. Hyperbola is very similar. We'll get into the equations in a little bit. All right, so those are the shapes, these are the four shapes that we're going to look at. Because we've done so much with parabolas, we're really not going to focus on the parabolas a whole lot. We'll focus mainly on the ellipse and the hyperbola. We'll cover the circle a little bit and the parabola a little bit. Okay, so let's go ahead and get started in our notes. So back to our parametrics, when we're graphing parametric functions. Now, we've already covered this circle in the last one when we have the number in front of your cosine t and in front of your sine t. When those are the same, that's your radius, and that's going to give you a circle. So your vertical radius here is 5 and your horizontal radius is 5. Okay. Now what happens if they're not the same numbers? Notice this example, your radius for your horizontal radius is a 5, but your vertical radius is an 8. Well, when that happens, you get an ellipse. Okay, so let's move back to here. So when we have this type of angle, anytime there's an angle like this, you're going to get an ellipse. It's going to be longer, either longer vertically or longer horizontally. Okay, and so notice with this next example, you have a radius of 8 and a radius of 5 now again, but you're switching it, so it's horizontally it's longer than it is vertically. Okay, so those are your ellipses, ellipses, I don't know. That's why I'm not an English major. So basically, for your parametric functions, when your radii are not the same, when one of them is bigger or smaller than the other one, then you're going to have an ellipse. Okay, so notice now here we've got tangent t and secant t. So what kind of shapes are we going to get there? Well, if you graph it, that's where you get your hyperbolas. Okay, so over here, this shape right here, the hyperbolas, okay, we can graph that with a tangent t and secant t. Okay, and so that gives us if you only look at the top part or only look at the bottom part, it just looks like a parabola. But because we have tangent t and secant t, we have a hyperbola. Okay, and so notice that here your x is tangent and your y is secant, and my hyperbolas are opening up and down. Well, what happens if x is secant equals secant t and y equals tangent t? Okay, it actually changes the orientation. It kind of rotates that hyperbola around. So instead of opening up and down, you're opening left and right. All right, so let's go through just a little bit, and I'm really hoping I included this page in your notes. If not, find a blank space somewhere to write it down. I'm really, really hoping you have it. Anyway, so for an ellipse, can be graphed with parametric equations in the following form. X equals h plus a times cosine t, and y equals k plus b times sine t. Okay, so we're used to the h and the k with this circle that told us where the center of the circle is. Well, it's also going to tell us where the center of the ellipse is. So the h and the k, those are the coordinates for the ellipse. Your h is always your x value, your k is always your y value. Okay, well, what does the a and b do? If this was a circle, if these values were the same, it would be the radius of your circle. But because we have an ellipse, it's going to tell us the radius of our ellipse. Okay, so, and the A is always going to be your horizontal radius, and your B is always going to be your vertical radius. Okay, always, always, always. You never, like if this, let's say that this value was a 2, you would not put a 2 right here in the X formula, okay? And then the H and the K, that's the center of your ellipse. Okay. I think one more page. Let's see. Do we have 2 more? Yeah, 2 more. Sorry. All right. So now what happens if you have a hyperbola? So this looks really strange for you guys. So the red lines, those are the only lines that are going to show up in your graph. Okay. But let's say this was a problem where we have the graph and they tell us where each of these points are. And they tell us the center, the point that's directly in between the 2 vertices here. Okay, and same thing over here. Well, we can create parametric functions from our graph. Okay, so the way this little dotted box is created is they take a line and they just draw a line straight across from the vertex here and the vertex here. Okay, just a line straight across. And then this line here is the asymptote. Okay, so it's an oblique or a diagonal asymptote. This hyperbola here is not going to go past this dotted line, and the hyperbola up here is not going to go past these diagonal lines at all. Okay, so then we now have the 4 corners of a box. Okay, and to get the formula for my x, remember x is your horizontal equation. Okay, to get your h or your k, you want to know how far is the horizontal distance from the center of this point to the edge of this dotted line. So if you look on the graph, it looks like it's 2 units, and oops, dang it, I messed it up. So sorry, this is the center, this is your x value, so that's 3, because from the center of from the origin it goes over 3. And then yes, so from here to the edge of your line, and that's 2 units. From here to the edge of your dotted line here is 2 units. So your radius is 2. Okay. So for this hyperbola, the x formula is going to be 3 plus 2 times tangent t, because we're moving to the right 3. That's where we get that 3. And then from the center of this point to the edge of the dotted line is 2. All right, so now let's see if you can figure out the y values. So we're moving up 1, and then from the center to our dotted line down here is 1, 2, 3, 4 units. So I'm guessing it'll be a y equals 1 plus 4t, 4 times secant t, excuse me, okay? And then the same thing over here. Now, I will tell you that we're going to have secant in my x formula. So notice over here it's in the y formula, and the tangent is in the x formula. Well, that's because we're moving, this hyperbola is going up and down. But these equations over here, whoops, your secant is in the x formula and tangents in the y formula, because our hyperbolas are opening to the left and to the right. I'll show you I'll explain a little bit more about that in a minute. All right, so let's see what the rest of our x formula is. Let's see. All right. So for horizontally, my center is just going to be 0. So I'm not going to add anything to this secant t. But my radius is 1, 2, 3 units over. Okay. So it's going to be 3 times secant t. Now this equation here, the y equation, I've moved up 2 units, so I'm going to have a 2 plus whatever my vertical radius is. Let's see, it's 1, 2, 3, 4, 5. So it should be 2 plus 5 times tangent t. Okay, so that's how I get my parametric function for my secant, or sorry, for hyperbolas. And now how can we know whether we're using tangent with x or secant with x here? Well, it depends on which way your graphs are opening up. Okay, so how to decide which equation, x or y, contains tangent t and which contains secant t? I'm going to delete that. If the hyperbola's branches open up and down, then x has tangent and y has secant. Okay, if the hyperbola's branches open left and right, then x has secant and y has tangent. I don't know if there's any easy way for you guys to remember that, but just make sure you have this information in your notes and you know where to find it, so that when you have a problem and you have to figure out which way it's opening up, left or right or up and down, you can do so. Okay, write the general forms of the parametric equations as of a hyperbola. This is, hold on, let me delete this. Okay, so if your hyperbola opens vertically, in other words, up and down, your h and your k are going to be here, a and b. This is your horizontal radius, your vertical radius, and then tangent and secant. Same thing over here. The only difference is whether it's opening up and down or left and right here, up and down here. That will be your secant and tangent. All right, I believe that's it. Yep. All right, so not everybody has to watch this video, just people that were absent on Tuesday, April 28th. All right, bye guys.